Welcome to the deep dive. Today we're unpacking this really paradigm-shifting paper from September 2026.
Yeah, published in the journal Cell by Liu and colleagues.
Exactly. And our mission for this deep dive is to figure out how this AI system, they call it Oncoformer, is basically rewriting the rules of cancer diagnostics using, honestly, the most boring data imaginable.
Right, the stuff you'd never think twice about.
Yeah. So if you're listening, picture this. You go in for your basic annual physical, you sit on that crinkly paper on the exam table. A nurse wraps a cuff around your arm to check your blood pressure. Maybe they draw a standard vial of blood for a routine panel, or they send you down the hall for just a basic chest x-ray.
Just standard operating procedure.
Exactly. But what if I told you that those incredibly basic data points could tell an oncologist your exact cancer stage, or like precisely how you'll respond to chemotherapy without needing an invasive biopsy right away?
I mean, it sounds like we're jumping straight into science fiction, but this is rapidly becoming our clinical reality.
It's why.
It is. And to understand why this paper is so monumental, we really have to look at the stakes here. The gap between early and late stage cancer detection often comes down to one, honestly, tragic bottleneck.
Access, right.
Exactly. The sheer cost and limited accessibility of advanced diagnostics. We're talking about highly specialized full-body PET scans or complex tissue biopsies that require a whole surgical suite.
Which most people just don't get routinely.
No. Millions of people simply do not have access to those resources until they're already showing severe symptoms. So what this paper attempts to do is bridge that massive diagnostic gap using the data trails we're already leaving behind.
Okay, so we've got a patient's routine physical data. How on earth does a basic, cholesterol check or a standard chest x-ray turn into this highly advanced cancer prediction tool?
Well, before we look at what the AI predicts, we need to understand exactly what kind of data is feeding this system.
The raw materials?
Right, the raw materials. The paper emphasizes that the model relies on longitudinal inputs, specifically time series electronic health record, or EHR, data.
Okay, longitudinal, meaning over time, right?
Yes, longitudinal is the operative word here. We're not looking at a single snapshot of your health. We are looking at a movie.
A movie, I like that.
Yeah, so the system digests routine lab tests, things like your complete blood count, basic blood chemistry, coagulation panels alongside vital signs, like heart rate, blood pressure, your BMI.
The stuff they check literally every time you walk into a clinic.
Exactly. But critically, it looks at them chronologically. It maps out your data from, say, visit your very first recorded appointment all the way through to visit NA, which would be your most recent one.
And then they pair that timeline of numbers with standard chest x-rays.
They do.
I mean, I'm trying to wrap my head around this. For everyone listening, it's like a detective trying to solve a highly complex bank heist, right? But instead of using security footage or wiretaps, they're only allowed to use a suspect's grocery store receipts from 2018 and their local weather reports from yesterday.
That's a great way to put it.
How can these seemingly unrelated, incredibly basic data points possibly point to something as specific as a tumor?
Well, what's fascinating here is that it requires a fundamental shift in how we think about the disease itself.
What do you mean?
We naturally visualize cancer as a localized lump, right? Like a solitary, independent mass just growing in isolation somewhere in the body.
Yeah, that's usually how we picture it.
But biologically, cancer is a systemic disease. A growing tumor demands immense resources. So it forces the body to build new blood vessels, which throws off your coagulation markers.
Oh, wow.
Yeah, and it sheds proteins into the bloodstream, it consumes energy, which alters your metabolic chemistry, and it triggers this low-grade immune response.
So it's essentially leaving footprints all over your routine blood work.
Precisely. These biological actions cause microscopic ripples in your systemic environment over time.
But a human doctor couldn't possibly track all that, could they?
No, absolutely not. A human doctor simply cannot hold 10 years of subtle, seemingly random fluctuations across 40 different blood markers in their head to spot the trend. I mean, a tiny drop in hemoglobin here, a slight bump in a liver enzyme there.
To a human, it's just statistical noise.
Exactly. But to an algorithm tracking longitudinal shifts, it reveals a complex biological pattern.
Okay, let's lock that in for you listening. Let's do a quick recap. Oncoformer isn't looking for a tumor itself. It's looking for the systemic ripples the tumor causes over time, tracked through your everyday lab results and paired with standard x-rays.
Right.
But I mean, that presents a massive translation problem, doesn't it? A blood test from 3 years ago and a chest x-ray from yesterday are completely different data languages.
They are.
Like a standard algorithm would just crash trying to read text and pixels at the same time. How did Lou's team actually solve that?
So they engineered what's called a unified multimodal transformer architecture.
Okay, lots of big words there. Break that down for us.
Sure. The transformer part is actually the same underlying mathematical structure that powers advanced large language models. It's phenomenally good at understanding context and sequences.
Like ChatGPT, but for your medical records.
Basically, yeah. And multimodal means it can natively process different types of media simultaneously. To handle the translation problem you mentioned, it uses separate encoders.
Ah, okay. The paper mentions a text encoder and an image encoder. So the text encoder is processing the sequential lab tests and vitals, treating your 10-year medical history almost like a long unfolding sentence in a book.
Exactly. And the image encoder is specifically designed to process the structural pixels of the chest x-rays.
Okay, so they're separate at first.
Right. These encoders act as specialized translators, converting both the text history and the visual images into dense mathematical representations. We call those embeddings.
Embeddings.
Yeah. But then it has to merge them so the AI can see the whole patient as one entity.
How does it do that without scrambling the data?
To do this, they project these embeddings into a shared latent space using a technique called VAE, Enhanced Multimodal Fusion.
Okay, VAE. That stands for variational autoencoder, right?
It does.
Let's try to make that visual for the listener. Think of this latent space like a massive multidimensional map of human health. The VAE doesn't just memorize your raw lab numbers, it plots your medical history as a specific moving coordinate on this map.
That's a perfect image.
So healthy patient trajectories naturally cluster in one, shining city on the map, while hidden cancer trajectories slowly, mathematically drift toward another city. The AI isn't just reading numbers, it's watching your coordinate move across the landscape of disease.
That is an excellent analogy. The VAE smooths out the chaotic noise of medical data and organizes it based on underlying biological truth.
Which is necessary because medical data is a mess, isn't it?
Oh, notoriously messy. A blood test taken at a highly funded research hospital might look fundamentally different on paper than one taken at a rural clinic, purely because of the calibration of the machines they use or the way the software formats the data.
Right, which brings up the adversarial missingness and bias control mechanism in the paper. Now, adversarial sounds like a conflict.
It does sound aggressive.
Does that mean the text encoder and the image encoder are actively competing against each other, like to see which one can find the cancer first?
Not quite. They aren't competing to find cancer. They're actually competing against a mathematical referee that's hunting for bias.
For referee?
Yeah, so in machine learning, if you aren't careful, an AI will find the laziest way to get the right answer.
As we all do.
Right? Instead of learning what lung cancer actually looks like biologically, it might learn to recognize, say, the subtle digital watermark of the specific high-end X-ray machine used exclusively by the oncology ward of a famous hospital.
Oh, wow. Wait, really?
Yes, this happens all the time in AI research.
So the AI would effectively say, this X-ray has the visual signature of the oncology ward's machine. Therefore, this patient must have cancer. It completely bypasses the actual medicine and just memorizes hospital equipment.
Exactly, which would make the model completely useless in the real world. So the adversarial loss function sets up a game of cat and mouse.
Okay, how does the game work?
One part of the AI tries to predict the disease, while the referee part tries to predict which specific hospital the data came from.
Oh, I see.
If the referee can successfully identify the hospital, the whole system is heavily penalized. It is mathematically forced to suppress that cohort-specific information.
That's brilliant. So to succeed, it has to learn the universal underlying biological patterns of the disease, regardless of where the data was collected.
Exactly. And this architecture also inherently learns how to handle missing data, which is crucial because nobody's medical record is perfectly complete.
Okay, let's do another quick recap and pose the question to you, the listener. We've got this system using text and image encoders to plot your health on a multidimensional map, while a mathematical referee ensures it doesn't cheat by memorizing hospital watermarks.
A solid summary.
But to train an AI to build a map that accurate, I mean, you can't just feed it a few hundred patient files, right? How much data does it actually take to teach an AI the universal biological signature of cancer?
It requires an unprecedented scale of data. The sheer size of the study cohort in this paper is staggering. We were looking at over 4.1 million patients in total.
4.1 million, that's massive.
It really is.
And the paper breaks that down into three main groups, right? The COMPASS main cohort had over 2.8 million people. The COMPASS replication cohort had over 862,000. And then they externally validated the whole thing using the famous UK Biobank cohort, which added another 500,000 people.
Right. And to put that scale into perspective, that represents tens of millions of individual doctor visits and hundreds of millions of individual lab values spanning decades of human lives.
It's just an ocean of data.
Yeah. And they use this mountain of data to test the model's performance, measuring it with metrics called AUC and F1 scores.
Okay, AUC, area under the curve. Let's explain that, because AUC isn't just a simple accuracy grade out of 1.0, is it? It's a measure of high-stakes trade-offs.
Right, because in cancer screening, you are constantly balancing true positives against false positives.
Catching the cancer versus crying wolf.
Precisely.
Yeah.
Catching a hidden tumor, a true positive, is obviously life-saving. But a false positive means you are terrifying a perfectly healthy patient and potentially sending them in for a highly invasive, risky, and expensive tissue biopsy that they never actually needed.
Nobody wants that.
Right. So the AUC measures how well the AI maximizes the life-saving catches while minimizing the harmful false alarms. And the data here revealed a very clear trend.
Which was?
The model's performance significantly improves the more longitudinal data it has. It scales up dramatically as it gets access to 10 total visits and as the time range stretches from 6 months up to 10 full years of patient history.
Okay, here's where I have to push back a little bit.
Sure.
If the AI needs a 10-year history of doctor visits to reach its peak AUC performance, does that mean it's practically useless for a brand new patient? Like, if someone walks into a clinic for the very first time with no prior records, is Oncoformer just blind?
That is a really critical question, especially for healthcare equity. But the good news is, while performance absolutely peaks with a decade of history, the baseline accuracy, even at much shorter intervals, say, just 1 to 3 visits spanning 6 months, is still incredibly robust.
Okay, that's a relief.
Yeah, it vastly outperforms traditional baseline models, even with minimal data.
So even a single snapshot gives it enough clues to point the doctor in the right direction. But a full 10-year photo album makes it a master diagnostician.
Yes, and if we connect this to the bigger picture, what this really highlights on a systemic level is the immense hidden value of maintaining a continuous relationship with a primary care provider.
Because you're building that history.
Exactly. Every time you get your annual physical, you are banking data. You're establishing a personal baseline that makes algorithms like Oncoformer exponentially better at detecting anomalies and protecting you in the future.
Okay, so we have this massive, unbiased AI trained on millions of lifetimes of data. What is the actual output? Like, what does the doctor actually see on their screen?
Well, the paper shows it operates across 10 different highly prevalent cancer types.
Let me list those for the listener real quick. Lung, prostate, breast, liver, colorectal, esophageal, gastric, ovarian, cervical, and pancreatic cancer.
Right. But it doesn't just give a binary yes or no for cancer. I mean, that would be impressive, but clinically limited.
Yeah, you need more details.
Exactly. Oncoformer predicts the precise clinical staging of the disease, stage 1, 2, 3, 4.
And it goes even deeper than that, doesn't it? Breaking the staging down into the classic TNM system used by oncologists worldwide.
Yes, the TNM system is the gold standard.
For those unfamiliar, T stands for tumor size, N stands for lymph nodes, and M stands for metastasis, or basically how far it has spread. And Oncoformer actually predicts the T stage, which correlates incredibly highly with the actual pathological maximum diameter of the tumor.
It does.
For example, in breast cancer, the correlation coefficient was R equals 0.635. That is a remarkably strong prediction for an AI that hasn't actually physically measured or scanned the tumor itself.
It is astounding.
Yeah.
It also predicts the end stage by calculating a lymph node ratio.
Meaning it predicts how many nodes are likely positive for cancer.
Exactly. But honestly, the most profound capability is its prediction of the M stage. It identifies not just if the cancer has spread, but it predicts specific organ metastasis.
Okay, this is where I want to know the how. Because how can a routine blood panel tell an AI that a colorectal cancer has specifically spread to the liver? Or that a lung cancer has metastasized to the brain?
It comes back to that systemic footprint we talked about earlier.
Yeah.
Let's take the liver metastasis example.
Yeah.
If a primary colorectal tumor starts seeding cancer cells into the liver, the delicate architecture of the liver gets crowded and damaged.
Makes sense.
So the liver starts struggling to clear certain enzymes, like AST or ALT. Now, A human doctor might see a tiny fractional bump in those liver enzymes on a routine lab report and think, oh, maybe the patient drank a bit too much wine this weekend.
Right, because it's so subtle.
But the algorithm sees the whole board.
It sees the whole board.
Exactly. The algorithm looks at that tiny enzyme bump, cross-references it with a subtle 3-year decline in hemoglobin, factors in a slight change in the patient's BMI, and recognizes the distinct mathematical signature of liver metastasis.
Wow.
It connects dots that are just invisible to the human eye.
Think about the implications of that for a second. The AI is functionally performing a virtual full-body PET scan and a chest X-ray.
This is the true aha moment for modern triage. Consider how a patient typically moves through the system right now.
Okay, how does that look?
Well, they might come in complaining of vague fatigue. Their routine labs are just a little bit off, but nothing alarming. The doctor might suggest, let's watch and wait, come back in 6 months.
Which is standard practice.
It is. But 6 months later, the patient returns with severe pain, and it's stage 4.
Oh, man. But if Oncoformer is running in the background of that hospital's EHR system?
The entire timeline changes. The AI looks at those same slightly off routine labs, compares them to the patient's 10-year coordinate map in latent space, and sees the invisible signature of a stage 3 tumor.
It connects the dots.
Exactly. It immediately triggers an alert to the physician. Do not watch and wait. This patient needs an advanced PV scan today. It essentially eliminates the deadly guesswork of early triage.
I want you listening to really internalize that. Your standard checkup could act as a tripwire, instantly triggering life-saving advanced imaging months or even years before physical symptoms would normally prompt it.
A revolutionary.
It is. But diagnosing and staging the cancer is only half the battle, right? Once you know it's there, the ultimate question for any patient sitting in that oncology chair is, what do we do about it, and will the treatment actually work?
And that is arguably the most agonizing conversation in medicine. Chemotherapy and targeted therapies are incredibly taxing on the human body.
Brutal. Yeah.
Giving a patient a highly toxic drug that their specific tumor happens to be naturally resistant to is a devastating loss of critical time and a profound loss of quality of life.
Well, this paper tackles that nightmare head-on. Oncoformer doesn't just stage the cancer, it predicts treatment responses.
Yes.
It categorizes patients as either predicted sensitive or predicted resistant to specific therapies before the treatment ever even begins.
And they didn't just test this on mild interventions. They went after the heavy hitters across the board.
Yeah, let's list some of these.
They evaluated EGFR inhibitors used in non-small cell lung cancer, cetuximab in colorectal cancer, sorafenib for liver cancer.
And hormone-blocking treatments too, right?
Yes, critical ones, like endocrine therapy in breast cancer, androgen deprivation therapy, or ADT in prostate cancer, and olaparib in ovarian cancer.
I mean, the charts in this paper mapping this out are just wild. The AI essentially graphs the predicted tumor size change from the baseline over the coming months relative to the specific intervention.
It's unprecedented predictive power.
It's basically a flight simulator for cancer treatment. A doctor can test fly the chemotherapy inside the AI's virtual environment before ever putting a single drop of it into the patient's actual veins.
Which brings us to the immediate future of precision medicine. This raises an important question. If an algorithm can predict, with high statistical confidence, that a patient will be resistant to a brutal drug like sorafenib using just their baseline routine data, we are entering an era of toxicity-sparing medicine.
Toxicity-sparing. And let's emphasize the emotional weight of that. This means no more spending your last 6 or 12 months of life violently ill from a drug that was mathematically destined to fail. That isn't just an improvement in a data point. That is giving families their time back. It's saving the patient from a biological battle they cannot win, so they preserve their strength for the alternative treatments or clinical trials that might actually save them.
It is a profound preservation of human dignity. And the model extends this foresight into prognosis predictions as well.
How so?
By inferring specific tumor markers from the routine data. Markers like CA125 for ovarian cancer, CEA for colon cancer, or AFP for liver cancer, it uses those to map out recurrence-free survival curves.
So it literally graphs the likely future trajectory of the patient's survival over time.
Yes. By synthesizing millions of past patient journeys, the AI acts as a compass for the individual's future, empowering both the physician and the patient to make profoundly informed decisions about their care and their timelines.
Okay, let's bring this all together for a final recap. We started with the most mundane doctor's appointment imaginable. A blood pressure cuff, a vial of blood, a chest x-ray.
Some basic.
Right. We explored how the Oncoformer uses a multimodal transformer architecture to fuse that time series EHR data together, translating text and images into a multidimensional map of human health using that VAE latent space.
Yeah.
We saw how it uses an adversarial referee to mathematically strip away the biases of specific hospitals, learning the true biological nature of the disease from an unfathomable data set of over 4 million people.
And from those raw basic materials, it achieves the remarkable, highly precise pan-cancer staging, predicting tumor size and identifying specific organ metastasis, plotting out simulated treatment response maps, and drawing survival predictions to guide clinical care.
Think about that the next time you go to the doctor. Every time you roll up your sleeve and give a vial of blood or step on a scale, you are not just getting a one-off checkup, you are writing a sentence in your biological longitudinal trajectory.
That's a great way to view it.
You're writing a story that, thanks to breakthroughs like Oncoformer, AI is finally learning how to read.
It represents a total paradigm shift in how we value baseline medical data. Your routine history is no longer just a static record locked in a filing cabinet. It's an active, life-saving diagnostic tool.
It really is, and I want to leave you, the listener, with a final thought to mull over.
Oh, this is a good one.
If an AI system can piece together the exact stage of a hidden pancreatic or lung tumor, or predict the failure of a specific chemotherapy from just a basic blood panel and a history of routine x-rays, what other invisible trajectories are hiding in our everyday medical records right now?
It's a huge question.
Are the early, microscopic whispers of Alzheimer's or severe autoimmune diseases, or even the fundamental biological markers of aging itself, already written in those routine lab results, just waiting for the right algorithm to decode them? We will see you next time on The Deep Dive.